Welcome back. We're going to continue our discussion on stoichiometry. And I have a problem for you. This is working backwards. So you can do two things. You can just not even pause and continue to watch and see how I solve the whole problem. Or you know how to do going forward to solve the whole problem like we did in the previous video in its entirety. If you know how to do it forward, I'm sure you can do it backwards. Okay, so there's two things, like I said, you can do. One is just pause the video at this point, write the question down, solve the problem, and then continue watching it to see if you got it right. Or you can just continue to watch it all the way through and then see if you understand it. If not, write down what questions you have and bring them to class when you come. All right, so the question says if 2.5 gram of iron is produced in a thermite reaction, what mass of iron 3 oxide and aluminum was used in carrying out the reaction? That is, if you understand the question, what it's asking is, we know this right here is 2.5 grams. In the previous problem, we learned how to calculate the mass of iron that would be produced. But here I'm telling you, if I have 2.5 grams, how much of each of the two reactants would have been used to get 2.5 gram yield, right? It's very, very simple. Again, you still have to figure out the number of moles, but the first thing you gotta do before you do any of these problems is balance the equation. And since I'm being consistent using the same single example, you already know the answer. This would be 2, and this would be 2. An unbalanced equation will never give you the right answer, and you're probably just wasting time trying to solve the problem, waste energy, time, and you would never be able to get the right answer. So the first thing on your mind should be, do I have a balanced equation? And I've already told you, I would never give you a balanced equation. So you've got to go get the equation balanced. All right, check. Equation's balanced now. Now, if you notice, unlike the previous problem where we had two separate masses for each of the reactant, here we only have mass of one of the products because, again, if we could have done it for aluminum oxide, but it really doesn't matter. We're just doing a problem. Okay, so that means whatever information given is your given information, so you're starting with iron. Please don't just interchangeably use iron for iron oxide or just the way you want. Things have to be written a certain way, then only you'll be able to solve the problem right. And given information is always accompanied by 1. Now, as I said, we would still be using the mole ratio in the same exact third column, but this time around, since we're starting with grams, we still have to get the moles of this iron, and I know that it's 56 grams over 1 mole of iron. Please write the unit and the actual substance, so it makes your life way simple when you want to cancel them. And then we want actually moles of each of this reactant, right? You cannot write them both in iron oxide or both of them in aluminum. I'm going to start with, so I want to figure out moles of one of the reactant first, so I'm going to write that, and then I'm going to say this is where I'm going to put my third piece of information, which is the mole ratio. Okay. Now, since we are going backwards, we're going to treat our products as reactants and our reactants as products. That means for every 2 moles or 2 parts of iron, because you cannot put that on the top, you're going backwards. So we want to be able to get rid of this, and for that you have 1 mole of iron oxide. And that means, if you get the calculator, it's 2.5 over 56 and divided by 2. So it's 0.0223 moles. All right, we're going to do the same this time for the second reactant, which is aluminum. So we're again going to start with 2.5 grams of iron, and that's your given information. So to complete the problem, we'll just put a 1. And the molar mass of aluminum, I believe, what did I say, 27? I think I said 27. It's 27. I'm sorry, this should still be for iron, right? Because we're still dealing with iron. So it's 56 grams over 1 mole of iron. And then we have to put 1 for every 2 moles of iron. Okay, there will be 2 moles of aluminum. Okay, so this cancels out, this cancels out. So it's here. So we're left with, I'm going to get a different color again. Maybe it's pink, maybe darker pink. All right, so moles of aluminum. And that would be 2.5 over 56 divided by 1, which is the same. So it's 0.0446 moles. Now again, we have to figure out the limiting reactant to know how much of each of this you would have started with, right? So, but only when you go in the forward direction, we have to pick the least number and all that stuff. But when you go back, you know, this is what actually had controlled, right, the amount of iron that you had made, right? Now, if you remember when we did the actual problem, the masses were different, and then we used the appropriate, you know, molar mass to get the answer, right? So when you're going back, I don't think you have to. So this is your given information, right? And then you multiply it by the molar mass of iron oxide, which is 160 grams over 1 mole. And that will give you the answer. And here it's 1. And then aluminum is 27 grams over 1 mole. Right? Again, you don't need to pick the least of the two because we're only trying to determine what was the mass of the two, right? So you do not have to pick the lowest of the two, right? Because how much you start with is entirely up to you, okay? How much you make is the only thing that's not in your control. How much you start with is entirely up to you. Now, if I have more aluminum powder, I'll use more aluminum powder. If I have more iron oxide powder, I'll use more iron oxide powder. All right, so we're almost at the end of the problem. So that means we multiply the 0.023 times 160. So this is 3.6 grams of iron oxide. I forgot to write the formula here. And this is aluminum. So that's 0.0446 times 27. You started with 1.20 grams of. So when you're going backwards, you do not have to determine which one is the smallest of the two. You just get them. And then, because, why are we doing this? Because we're keeping this constant. You see this right here? This 2.5 is constant. That's why. If this number is different, then I don't think you have any way of controlling the problem. It's just going to be chaos. But because we're starting with the same information for both calculations at the very top, the same number, I don't think you have to again go back, pick which one is the least, but this is how you do the problem. All right? That's why I gave you two choices at the start, because if you have opted for the first option where I'm going to give it a shot, if you have in fact circled, which again, something I don't expect you to know before you did the problem, but you probably circled the least of the two and then multiplied it, okay? But because we're going backwards, I don't think you have to necessarily do the least of the two, because of course, like I said, how much you start with is entirely up to you, all right? So this is how you solve a reverse stoichiometry problem. The one we did earlier is usually the conventional one that you probably can see on any generalized exam. across the board. But the reverse stoichiometry is something you mostly often see in a classroom setting, rarely on a professional exam, but doesn't mean they cannot ask. Okay, so that's why I'm teaching you this, so that you have that information handy to tackle the problem. All right, so that's solids. And then the next thing I'm going to teach you is actually solutions, means something in a liquid form. But I won't get too far into the concept, because something that we will come back again in the second semester chemistry course when we learn this stuff. But this time I want to keep it purely from a stoichiometric perspective, not so much from the solutions perspective. Okay, so stay tuned for that video. I'll see you back then. Goodbye.